What going on? But all the last three things are all. Yes, just.
Yeah, we're triple booked tonight as well. All for Dash actually today.
Really?
Typical oldest child. He has a track meet that overlaps with his baseball game, both of which overlap with his open house.
Yes.
So while we value academics, we won't be going to open house because
Yeah.
we know what he's doing in school.
Will you be go?
He did not tell his track coaches in time before they assigned events that he would be missing. So he's going to track and missing baseball, and he's not pleased about that.
Yeah.
But it's still a developmental game. This one doesn't count for their records, so
Okay.
he'll be fine.
Yeah.
He's just not pleased about it. And then he got put in the very last event. He's running the 4x4 relay at the very end, so he's probably going to still be running at 6:30, and the baseball game starts at 5:30.
Yeah.
So he might make the end of the baseball game, but we're not counting on it.
Yeah. Are they in the same school?
Nope.
Oh.
Track meets at Whitell. At least it's in the basin. Yeah.
Okay.
Because last week track meet was in Carson City, and the week before that was in Galena, near Mount Rose Highway. So at least it's close this time. Based on what I can see, I think they make their entire middle school like be part of the track team, because there was like 12 people for Whitell, and they only have like 12 people in middle school. So yeah, pretty much. All right. Let's review the nucleophilic addition of carbonyls. This is the last thing we covered the other day. So our proton transfer was our first step because we're under acidic conditions. So we protonate that carbonyl lone pair, which makes our carbonyl bond, our carbon-oxygen pi bond, easier to break. Because we've got an oxygen with a positive charge, so it's not as strong of a pi bond. So a nucleophile can then come in here and attach and move the pi bond up to the oxygen, so we get the alcohol with the nucleophile attached. All right, so what is different if it's under basic conditions?
It's nucleophile.
Exactly. So acidic conditions mean you're only going to make positively charged intermediates, and basic conditions means you're only going to make negatively charged intermediates. That's a pretty broad statement, but it's for the most part true. You can have negative intermediates, but it's pretty rare and short-lived in acidic conditions. So if it's basic conditions, we'd be looking at nucleophile attacks first. To make the negatively charged intermediate, and then we do a proton transfer from water or whatever else is around, whatever proton source is around. Sometimes the proton source is just the conjugate acid of the nucleophile, right? If our nucleophile is hydroxide, then our proton source is probably going to be water. But if our nucleophile is I, NH2 with a negative charge, then our proton source might be NH2 minus. But whatever you have around that can act as an acid, which oftentimes is also just a solvent molecule. All right. So this is where we ended the other day. We drew both of these mechanisms. So I'm not going to go back through them today, unless we want to. Okay. All right, so we're gonna talk about some specific cases with this that wind up being useful for various reasons, or because they show up all the time in nature. So if you have water acting as the nucleophile, we actually get a diol as our reaction. So if we have acetone reacting with water, right at the reaction, including the product, let's give it a go. Well, you can start by writing products based on the description. Let's get practice, then try running this. I said under acidic conditions, right? I just erased that so I had room, but it said under acidic conditions. So under acidic conditions, we're not actually just going to have H2O around, right? Acidic conditions means we have hydronium. So there's our intermediate. So in this case, we have one extra step in there. Right, because we can't have, if we're under acidic conditions, we can't have hydroxide act as our nucleophile. we have water acting as a nucleophile, which means we add a whole water molecule, which means one more proton transfer step at the end. So what's always around?
Water.
Water, especially in this case. So we have another water molecule around. And so like we've been noticing, nothing new about this really, other than the functional group that we started with. Other than those weird cycle additions and in the electrocyclic reactions at the end of last term, we really, I guess, in free radicals. Other than those cases, everything else we see is those 4 basic mechanism steps that we started with back in September.
Yeah.
Proton transfers, nucleophile attacks, leaving group leaves, rearrangement. Right, can we predict which side of this reaction? I'm going to erase the mechanism so that we can see these better. We're good with that? If we look at the products and the reactants, do we have a sense of what might be favored? Water and acetone versus this propane diol. Their actual reaction, or net reaction, is just going to look like this, right?
This is the main. It's under oxygen phase.
Well, so this is. Make sure I don't use this. Is I think we just call this the diol formation from a ketone. Aldehydes will do this too to some extent, and we'll see a more specific example of this where it's not just water in a second. But yeah, if we do a hydration of acetone, depends a little bit on the conditions, right? It's definitely an equilibrium reaction. If we were at high temperatures, which side would we favor? Why?
Products. Are favored.
Why?
When.
What changes at high temperature?
Chaos, chaos on the answer.
Yeah. Why not? Everything comes back to this, right?
Yeah.
So when temperature goes up, the entropy piece matters more, right?
Yeah.
Which side has more entropy? Not in this case. The side with more pieces. So if we had it written backwards, then yeah, sure, products. But it's really what we're looking at, which one has more individual pieces, because that's going to have more randomness, more configurations. So high temperatures, we're definitely in favor of this. Low temperatures, our enthalpy term, delta H, is going to favor this because there's no pi bonds. Remember, sigma bonds pretty much across the board are more stable than pi bonds. So at low temperatures, the delta H piece becomes more important. And so we would expect this to dominate. But it's definitely a sliding scale. We can change the conditions. If we have anhydrous acetone with very few of these molecules around, obviously we're not going to make very much product. If you add a whole bunch of water to acetone, especially under acidic conditions or basic conditions, you're going to push the equilibrium this way. But without water you're gonna say mostly as the ketone.
Why do you always do that? It's so pronounced.
And these are your pearls.
Do you like that boy in that book that we're gonna look at? Oh, yeah.
Stories from Wayside School.
He is the girl with blonde curls in class and by pulling on and then
She
watching
has
her.
big bits.
Yeah.
Pulls the big bits.
Yeah.
Falls out the window, standing by the window.
Sorry, there's. If you guys not remember that book, did you guys read the book? They built the school sideways. It was supposed to be a flat school, but the contractors built it sideways, so it's a skyscraper. In like the third grade classroom, it's on the top floor.
Perfect. Like, I completely forgot about it, but like you saying this, it's not the first time I heard it.
So the one about the boy who always pulls the girl's pigtails is he gets in trouble for pulling on her pigtails. They have a big argument, and then at one point he falls out the window on the top floor of the skyscraper school. And she has long pigtails, so she sticks her hair out the window. It says, "Pull the pigtails." You can pull him back in.
But she has blonde hair, right?
I don't remember the color there. That was a very like weird. It was a very weird, contrived situation, and that's what stuck with me. I don't remember the color hair though. Sideways Stories from Wayside School. The name of the teacher was funny too. Anyway.
It says, remember when she had me pick colors for her lip gloss? They came in the mail and she's obsessed.
Well done. Did you do an unboxing video?
No, just a live unboxing. Kind of. So I kind of did the unboxing video.
The Kuiper has found, or Laura found a YouTuber who does blind box openings of like little toys, and she's pretty funny about it. And so Kuiper loves that right now. So he's all about the unboxing videos.
They're very.
All right, let's talk about a more specific application of this. And this is instead of using water to make a diol, if we use an alcohol as our nucleophile, this is actually a reaction that happens all the time in biological situations. Because most of our sugars, actually all of our sugars, have a class 2 carbonyl when they're in their open chain form.
I mean, the last one was called diol formation. It's just all.
Hemiacetal or acetal formation. So the only way you really see this generally is when you have a class 2 carbonyl plus an alcohol. So if you say acetal formation or hemiacetal formation, that's what you're talking about.
This first one is hemiacetal and the second one is.
Correct. So the first thing that happens, you get a hemi means half, right? Like hemisphere. So a hemiacetal means you're halfway to an acetal. Acetal is when you have two ethers attached to the same carbon. So then a hemiacetal is when you broke into carbon oxygen pi bonds and have attached one ether to it. Right, so the same mechanism we've been looking at.
Two ethers attached to a pi bond, is that what you said? No.
Two ethers attached to the same carbon. And the mechanism is going to look identical to one we just did, except with an alcohol instead of water. Not the first time we've seen that too, right? Alcohols and waters react very similarly when they act as nucleophiles. So why might this show up and be important in biological contexts? Well, the structure of a glucose molecule. The way that biologists often write it, 1, 2, 3, 4, 5, 6. And I'm going to mess up the stereochemistry here. But basically, glucose has some OHs to the right, some OHs to the left. So glucose looks something like this. This is a big long molecule that has both a class 2 carbonyl and a bunch of alcohols. So it'll do this within the same molecule. What's the most stable size ring in organic chemistry?
6.
6, right? Which alcohol is going to attach here to give us a 6-sided ring?
There you go.
That one? So if we have a total of 6 carbons, if the oxygen then attaches, we got 6 carbons and an oxygen all in the same ring. So you're close. One fewer. Second to last one. If the second to last carbon or second to last oxygen comes in and attaches, we get a 6-sided ring that's going to look something like this. So this is the CH2OH, our last carbon. Then we've got a bunch of other, again, the stereochemistry I don't remember off the top of my head, but it's going to look something like this. So this is the mechanism why we see sugars drawn both in their what we call the open chain form and in their ring form. Both of these are glucose.
Yeah.
But when you put glucose in its open chain form into an aqueous environment, especially if it's a little acidic, it'll spontaneously form the ring structure. And whether this last point is up or down, or this oxygen in particular, this is the oxygen that was the carbonyl, right? Because this oxygen is this oxygen. So it came all the way around and attached there, which means this aldehyde turned into an OH group. It's OH group attached right here. So this exact, with the stereochemistry of this one, this is sp2, right? It's just planar. This OH can attack top or bottom, right? So really we're going to get both stereoisomers, one with the OH down and one with the OH up. The one that is right-handed, that is an R conformer, is one that's called dextrose. Dextrose is just a specific stereoisomer of glucose. The left-handed, I don't think we have a name for the left-handed form of glucose. Maybe levorose or something, but
Do you think dextrose has?
yeah.
Aren't you, like, some people complain with dextrose?
Some people claim they don't anyway. I don't think that you can by taste tell the difference between the right-handed and the left-handed. I mean, some things you can, but I don't think so for sugar, because as soon as you dissolve it in water, it doesn't stay as pure dextrose anymore, because as soon as you dissolve it in water, this is a reversible reaction.
Yeah.
So yeah, it might start as dextrose because sugar beets predominantly make dextrose, say. So when you purify sugar from sugar beets, you might get mostly dextrose or sugar cane or whatever. But when you put it in water, it's immediately going to start going back and forth between these two, and you're going to get a 50-50 mixture of the right-handed and left-hand version. So saying that you're adding dextrose as the ingredient is really just saying you're adding glucose. And it's not really any different than adding the other form of glucose.
But people even doesn't vote that.
Right.
It's glucose in it.
People have a problem understanding that the chemical name is still natural.
Yeah.
If you call it there's, pet peeve of mine, it's the naturalistic fallacy. Just because you called it by its chemical name doesn't mean it's bad for you.
Yes.
And everything in moderation.
Oxygen's already killing you anyway.
Oxygen's already killing you anyway. So you're not getting rid of the big carcinogen, so you might as well just manage your risk of the other ones.
Your arrow looks like this. What? This one coming from the level there.
Okay. I'll accept that.
That's all. That's all.
I'll accept your feedback. Alright, so this is also why when if you have sugar in general, there's another reaction that can happen where this oxygen can act as a nucleophile to another glucose molecule to make what's called a dimer. So if we haven't talked about polymers really, but polymers is when you take a bunch of small units and repeat them to make a larger structure. Right? So picture taking the same like Lego piece of 4x2 brick. And if you have enough of those, you range them into a much larger shape, right? You do the same thing with glucose molecules, you get all sorts of other stuff. Starch is just a whole bunch of these attached, where this oxygen acts as a nucleophile and attaches to, is it a 1,4? I think it attaches here. This one actually is probably down, not up, now that I think about it. Because I believe that this attaches to there on the next oxygen, on the next glucose, and you get a larger chain. So starch is just a whole bunch of those in a row. In fact, so is cellulose. But we can digest starch. We can't digest cellulose, right? Because cellulose has this OH attaching here, I want to say. In our bodies, mammals do not have, actually eukaryotes, do not have the enzymes to be able to break down a 1,2 glycosidic linkage. It's called a glyco means sugar in Greek. Glycosidic means that you basically did an addition reaction between two sugars. So we can't break down a 1,2 glycosidic linkage, but we can break down a 1,4 glycosidic. So starch is digestible, cellulose is not, by any eukaryotes that I'm aware of, which is why almost nothing is just grass. Right? Your horses can't survive on grass. What can? Cows,
Yeah.
goats, sheep.
I think they answer.
They'll eat it, but there's not enough calories and nutrients for them to survive on it long term, which is why you have to feed them hay and alfalfa and stuff. Because they can break down starches, but not the ruminants. The ruminants are the animals. They forage, and specifically, they're the ones with multiple stomachs.
Okay.
Right? And so the multiple stomachs, what that actually does is the first stomach that's full of rocks, supposedly, it's actually just a bunch of calcium carbonate. So it is like limestone. But it's produced by the body. They don't go eating rocks to do it.
Like birds hear it chase.
Birds eat rocks. And that's serving a different purpose, if I remember correctly. I think that's because they have a mineral deficiency. And they can actually get some of the minerals by eating the rocks. Kind of like that's eating salt, really.
Yeah.
They're also just kind of stupid. But the first stomach that has the stones in it basically grinds up the cell walls of everything to kind of expose all the pieces. And the next stomach is not actually a true stomach. It's just basically a place where you've got a whole bunch of microbes that can digest cellulose. And in doing so, it goes through a fermentation process where it digests the cellulose, produces a little bit of like lactic acid and some other molecules that eukaryotes can digest. So basically, it's actually the bacteria that do the digesting of the cellulose, and then the cows and goats just live on what the bacteria has left over. I've always just found that fascinating because it's really just still glucose,
Yeah.
just linked in a different way. And if you only link two of them, this is where we started with that digression. If you only have two sugar molecules, regardless of what they are, it's called a dimer. So a monomer means when you have one piece of something.
Yeah.
A dimer is when you have two of them. Diamonds too, right?
Yeah.
And then a polymer means a whole tube. A dimer of sugar molecules is usually another sugar, something else that tastes sweet. So like maltose, lactose, sucrose are the three most common ones. Actually, I think maltose is a trimer. But basically, if you take a glucose and a fructose, you make sucrose, which is table sugar.
Oh, yeah.
If you take two glucoses and link them together, there's I'm trying to think which one that was. I'm not brushed up on my carbohydrate nomenclature. So don't hold me to that. But I was just wanted to point out that similar reactions that do all of these different linkages, just the ones where you link to where you make a dimer or a polymer, they're less reversible. And that's why we need enzymes to break them down. This is reversible. The hemiacetal formation is totally reversible under any condition, basically. It's just even a little bit acidic or a little bit basic. It'll go back and forth.
But not acid.
But not acetals. Because if you make an acetal, you actually have to have another alcohol come in and attach to the same carbon. So if we had a way of removing water from the situation, we could drive this second reaction forward. Like we had another isopropyl alcohol come in and attach here. Now we have three good leaving groups attached to the same carbon.
Yeah.
Depending on the condition, it'll either be the isopropyl alcohol that leaves again. And then we're back right here where we started. So no point writing that out reaction, right? But if you have your OH leaving group, which usually under a basic or acidic conditions means we'd have to protonate it and then it would leave water. We wind up with the acetal. Right, so for the most part, both for the diol formation and for hemiacetal and acetal formation, the carbonyl form is favored. Because of the entropy mostly. But if you change the conditions, or if you look at the really, really simple molecules for formaldehyde is a really good example. Formaldehyde is the smallest possible aldehyde. So how many carbons would be in the smallest possible aldehyde? An aldehyde looks like this.
Wait, is that a good?
So that would be ethanaldehyde. Ethanal. It's just one. That's like a double aldehyde almost, right? Because it's an aldehyde on that direction and on that direction. It has no electron domain curves. So formaldehyde is our smallest possible. And because it's so reactive, there's a few things that it'll do that most things won't. So formaldehyde will actually favor the acid or favor the diol form. So when you're doing a dissection in A and P, you smell the formaldehyde, you're smelling the formaldehyde, but it's not actually present as formaldehyde. Because when you put formaldehyde in with ethanol, I believe it's a ethanol formaldehyde solution. You make an acetal first, or hemiacetal first. So then we have something that looks like that, right?
That's what we're.
That's the hemiacetal form. It'll actually go one step further and do that again to make the acetal. So you actually have this and the hemiacetal form and the formaldehyde form all present in that mixture. If you just had formaldehyde and water, these would just be OHs. And you would make the diol. Because so if you look at the bottle in the stock room, for formaldehyde, it's actually called formalin. Because it's actually a mixture of formaldehyde and I can't remember if it's formaldehyde and ethanol or formaldehyde and water. Either way, it's usually present as either a diol or a hemiacetal or an acetal, some combination thereof. Does anybody remember where the form comes from? This is another good digression, just a small one. Form is before they use the IUPAC nomenclature for naming these, form meant one.
Oh, okay,
So formaldehyde is same thing as saying methanol.
yeah,
And it comes from a Greek word formica.
okay,
Formica is the Greek word for ant. Ants, the animal.
okay,
Because the first place they found formic acid was inside of ants. First place that
they're so tiny. How did you discover them?
so somebody realized they had an ant infestation in their kitchen. I'm assuming it was their kitchen, but you ever had that happen and you had like a whole trail of ants and you switch them all at the same time? They smell really distinct, right?
I didn't know, but okay,
Next time you have ants, pay attention to how it smells when you squish them.
okay.
That smell is formic acid.
Huh, okay,
Because insects don't have a circulatory system, right?
right,
Because they just have holes in their body that let air in. And so instead of having blood inside, they have a whole bunch of formic acid that helps preserve their enzymes. So formic acid, the name for formic acid comes from formica, ants, which then comes full circle because in the 80s there was a product they used for counters called formica. It was a polymer made from formic acid.
Okay.
So now you know where form comes from. It was from before they knew there was only a single carbon. They didn't know that formic acid was only a single carbon. But so now we would name it methanoic acid. Or instead of formaldehyde, IUPAC would say methanol. I always find the stories behind the common names help me remember the common names, and I think they're interesting anyway. So, all right. So here's a full mechanism drawn out. I'll just take a picture first.
James,
It's the same steps we've already drawn though, just twice in a row.
yeah,
And just like we've seen in the past, if you know what your landmarks are along the way, it makes the whole mechanism. You know that to get from the carbonyl to an acetal, you know you have to go through a hemiacetal first. Getting from here to here is not that tricky. And then getting from here to there, it's just the same thing again. A is, where do you see A?
on the arrows.
Oh, just a generic base, something, it's the conjugate base of a weak acid, so that's something we can accept for.
Right.
I don't know why they use A when it's acting as a base. I think B would make more sense, but for this particular mechanism, they didn't do that. So let's do some practice. If you have cyclopentanone with an acid catalyst in excess methanol, you can make the acetal. Try drawing out that mechanism.
I think we know if it's the, yeah, I'll ask probably what it. Is it one of its three distiller, or is it just like?
Yeah.
So what are like our indicators?
That it's gonna make, well,
Like we didn't learn what was on our arrow.
we have nucleophile and we have basic conditions. Basic conditions in a nucleophile with the class 2 carbonyl. It's either the acetal formation, just a specific case of the same mechanism we've been looking at. Right, so under acidic conditions, you start by, I'll do it verbally, give you a wait, or a clue. For under acidic conditions, first thing is to protonate the oxygen, the carbonyl oxygen. Then you have your nucleophile come in and attach the carbon
Acidic.
in acidic conditions. Basic conditions backwards. And then you and so then you've got an OH group that gets you your hemiacetal. Then your acetal formation, you just do it again. Protonate your oxygen again. Nucleophile attacks again. Your oxygen leaves as water. And there's a few other proton transfer steps in there, so give it a try.
So are we saying that it's acidic conditions?
We already have H2SO4 without acidic conditions, right?
That's it. Yes. H3O.
Sorry. Just as a generic acid, right, it probably wouldn't be there because otherwise we're trying to eliminate water. So yeah, so H2SO4. So that's attached to an oxygen, attached to,
We just did H dash. H.
that's fine. So that gives us almost to be hemiacetal.
Okay, yeah, we got there. But now I don't know what to do.
What do we have to do to get to the hemiacetal from there?
Oh, we do it again?
Not yet.
Well, no, okay, we have to get rid of the H.
So we had to pull a hydrogen off of the sulfuric acid for our first step, protonate, right? So if we want to deprotonate, we take the conjugate base, the hydrogen sulfate, and have that as base. That gets us to the acetal.
Now I'm gonna do this. That step. Again.
Exactly. But even simpler. Actually, before we can do that, we already have 4 bonds to carbons. We can't attack it yet. Unless we're ready for our leaving group to leave. So, this leaving group's not ready to leave yet.
So we have to make it H2O.
Exactly. Because we're under acidic conditions, we can't have hydroxide. But we can have water as leaving, so we protonate it first. So we just undo this thing we just did. To be back and forth between stage 3s and hemi, but I think we're all okay with that, right? Now we can have the other methanol come in. And your water loops. And once more. Last proton transfer. Just so we don't end up with positive charge on it. it becomes a little bit like doing the algebra by hand for a long substitution problem at this point, right? 'Cause it's just a matter of, okay, wait, I can't have a negatively charged universe, I have to do the proton transfer.
Yeah,
I can't have my nucleophile be negatively charged, so it has to be, my nucleophile has to attack in a neutral form and then do a proton transfer. It's really just crossing your T's, dotting your I's. It is. So, in the interest of repetition and practice, we'll take a break and then we'll do the second part.
second.
Well, sorry.
Oh, okay.
This one.
I go first. The paper, I want to try and left.
You know, you can take it out because it's technically.
Really? I didn't know that. That'd be nice.
I've gotten to the point where I just print, I have a laser printer at home, and so I just print graph paper, so sometimes I do hexagons. All right, see you in 10 minutes, come back at 11.
Nobody has graph paper anymore. Everybody used to have it. You're 100% you might have.
I can print some.
That was actually the theoretical field for. I definitely did it wrong, and I don't know what I did wrong, but
What are you getting for your theoretical yield?
to the -19, which is definitely not correct. Not percent yield today. The one, remember how for the final lab, we had to do a whole bunch of math to find it's that. Is it?
It's only 2 reactions though.
I mean, but mine is like no. So I don't even know if I need to do the math.
Go through the steps. You're going to wind up with single digit yield or maybe even less than a percent yield. But it shouldn't be 10 to the -19, especially for you, Riley, because you did get.
I know. Is that a minus somewhere? No. It's supposed to be, look, it just kept getting smaller and smaller and smaller. I think you're missing something.
So at some point, you were supposed to multiply by, like, divide by, to get your final grams, right? Oh. So double check your logic.
Okay. Well, but I moved it to the bottom because that's the only way. Sure.
Well, yeah.
That. This one is cancel that. These are your ending units.
Except this is the actual reaction, that reaction doesn't happen. So I think you got some extra reactions in that,
Okay,
could be part of it.
okay.
And actually, if you're getting a number that's way too small, that means your theoretical yield is way too large.
Okay.
So maybe you multiply by the molecular weight that you were supposed to divide instead of the other way around. So double check.
I think my mechanism is wrong. Because I'm doing the mechanism like. I don't think I did it very well. Because like every time we added diethyl ether, I was like, I don't know where this fits in.
It's just a solvent.
So it doesn't,
It
right?
doesn't-
Okay,
It's not part of it.
I didn't prove it.
Okay.
But it confused me for a while.
So your overall reaction was just, it was benzene, right? Or bromobenzene. So C6H5Br
Yes,
plus magnesium
yes.
makes our Grignard reagent C6H5MgBr.
No step, I had steps in between.
So for your mechanism, you should, but for your theoretical yield, you don't.
Oh. Maybe that's why I.
Because this is the first net reaction. And then the next part was you take the Grignard reagent plus CO2 and you make C6H5CO2H.
And that's.
That's not, neither is the mechanism. I'm glossing over the mechanism for this. These are the net reactions.
So the top one is a theoretical yield net reaction.
No, both of them together. Because the first one is making your Grignard reagent. The second one is using your Grignard reagent to make benzoic acid. So I think you're overthinking it because if everything's 1-to-1, this is our limiting reactant here. This is our limiting reactant for the second step, right? So if you know how many moles, so did we do it in grams or milliliters? Milliliters. So we use a density to go from milliliters of bromobenzene to grams of bromobenzene. Grams of bromobenzene to moles of C6H5Br. This is 1-to-1 stoichiometry, right? And so is this. So once you're in moles of bromobenzene, you can go straight to moles of product of benzoic acid. pH, CO2H. Grams of product. So if it took you more than, if I'm being generous, it might take half a page to do it, to show your steps,
Yeah,
but you were doing too much.
yes, I was. If I have time before it's actually due, I'll go back and redo this part.
Okay. I think it's not due till tomorrow, so if you have time.
You changed the date to like cancel. You like really pushed it back.
That was probably a mistake. I meant to make it Friday tomorrow.
Well, I have an exam tomorrow, so I might have time after because I always finish those.
Okay.
But I have a lot of stuff already submitted. So I don't know if you like get notifications when we submit things, but I submitted it like 5 different ways. Because I had like a picture of one thing and then a cam scan of another thing and then a document. There's a lot of different.
That's fine. That's okay. All right. I know I said we were going to repeat this, but I realized that we need to get to all the way to the last slide today, or else one of the quiz questions is not going to make sense. So we're going to skip the second mechanism here.
We'll do that for warm up on Tuesday.
Okay.
Right, so when we're talking about these hemiacetal or acetal formations, these are all equilibrium reactions. So just by controlling the situation, by removing water, by changing the temperature and changing concentrations and everything else, that's going to allow us to favor one side of the reaction versus the other. Right, so if we have lots of water present with our carbonyl, we're more likely to be in the carbonyl form. If we're removing water or we have lots of our alcohol, we're more likely to be in the hemiacetal or the acetal form. This winds up also being useful in synthesis because ethers are pretty non-reactive. Ethers we can't reduce or oxidize easily. So if we have something that we want to oxidize, but we want to keep one group from being oxidized or reduced, we can convert it to the acetal. And so for an example, let's say we've got an ester and an ether on the same molecule. Just remember that's an ester, ether. If we wanted to reduce the ester to an alcohol, we can do that with lithium aluminum hydride, but then we'd also convert this to an alcohol. If we want to keep the ketone but reduce the ester, we can convert the ketone to an acetal. Because esters don't go through the same acetal formation that ketones do or aldehydes do. So this first step right here, it's giving you all the pieces. After step one, our molecule is going to look substantially different. Because after step one, we're going to have something that looks like this. And so this is ethane diol, also called ethylene glycol. It's antifreeze. Antifreeze for a car is just ethane diol. And it has the advantage of being able to have both of its alcohols can react with the same carbon to make a 5-sided ring. So it's really convenient as a protecting group. So by saying, okay, we have a little bit of acid, ethylene glycol, and we're going to heat it so that we're driving off the water molecules. Then we get this as a product. After step one. Then we use lithium aluminum hydride. Lithium aluminum hydride will reduce any carbon oxygen pi bonds to the alcohols, right? So after step two, we get this. Does look like a little robot. And then the last step, by adding acid and more water back in, we're just going to take our protecting group and remove it, turn it back from the acetal back to being carbonate.
Okay.
Right, in the cases where you have class 1 carbonyls and class 2 carbonyls, if you want to react one of them but not the other, you're always going to have to do a protecting group.
That one is the protective group in this case? Yeah.
Yes. Because we took a functional group that is reactive, or a carbonyl group, and we turned it into something non-reactive.
reversibly, so that we could go backward. It looks like, you know what it looks like? You guys remember Invader Zim?
Yeah.
It was a precursor to the same type of people that like Rick and Morty liked Invader Zim before, when I was in high school and college. And
Wait,
it's a
is
little
that-
alien dude who looks like that. He's a little green alien guy with big eyes on the side of his head.
Was it like it was a cartoon?
Mm-hmm.
Were they on a spaceship?
Maybe. This guy.
Oh.
Anyway. All right. Staying on task now.
Let's talk about nitrogens. Because just like hemiacetal and cells, there's a few cases where we can convert a carbonyl into a different functional group we haven't seen before, using a nitrogen-based nucleophile. And so nitrogen-based nucleophiles, like an amine, we have a primary amine, or even just ammonia. It'll do the same thing as like a hemiacetal formation, except we call it a carbonylamine. Right? Carbon, OL for the alcohol with an amine. So it's just, a carbonylamine is just an amine attached to it. Thing is, when this rearranges, we don't just do that twice. It'll actually kick off the leaving group to make a carbon nitrogen double bond. Right, and so the carbon nitrogen double bond with another R group attached, or even if that's just another H, it's called an amine. Or an imine, depending on who you ask. Favorite day. This is one where I've heard it both ways, not to the point where I'm not actually sure if there's the right answer. Right, so it's the same basic step. The first thing is like mildly acidic conditions. So first thing, we protonate. Then our amine comes in and attaches here, which gives us our carbonylamine.
Amine, fatness, carbon.
Correct. So we've got this. And our nitrogen has a lone pair. Plus the negative proton transfers to H from the nitrogen, but we're used to that thing.
Yeah.
Under acidic conditions, we can still protonate this oxygen, right? Makes it a good leaving group. And so then we can just have, so if we have it protonated, we kick off the water molecule. And we form a carbon nitrogen compound. And as usual, I wrote it out in a sloppy way and then have it nice and neat on the next slide.
Are there gonna be multiple nitrogen miles?
We're gonna look at a specific case next, but for the most part, for nitrogen to be a nucleophile, it has to have a lone pair, which means mostly we're looking at emissions as our nitrogen files.
Like, does this have its own other name?
Iodine formation, ABE formation. And actually, there's a typo in this sentence. See if you can figure out where it is. We're under mildly acidic conditions. Yeah. You shouldn't have that. They should have done the proton step first.
So should we do that in our?
I would say so, or at least make a note of it. If they, the fact that they say mildly acidic conditions is actually really important here. Because if you're in mildly acidic conditions, you can potentially have that existing for a short amount of time. So I'd like to mark it down, but it's not the best way.
So we say just in H plus first.
Yeah, so first things first, your H plus attaches to the, or your oxygen drops to the plus. And then we add the nitrogen. So switch these first two steps. Why do we have to make sure it's mildly acidic? Why can't it be strongly acidic?
Cause strong makes it.
Yes,
Something else.
amines are good bases, right? They're relatively good at accepting H pluses. If we have this protonated, if we have R NH3 with a positive charge, can that act as a nucleophile? I don't like that orange color.
The return first step is just H, or do we do the HA thing?
You do. Yeah, that's something that is your proton source, but whatever your acid is, or you can just write hydronium as your acid.
Could it be just the HA thing?
I'd be fine with that. Especially if I specify what the acid is, you should use that acid.
Right.
But if it's just in generic cases, HA is fine. So this won't react. It won't react as a nucleophile.
Oh.
If it's under acidic conditions, because there's no lone pair.
Mm.
So we need it to be acidic so that we can protonate this.
Yeah.
But not too acidic. Or else this won't react.
Right.
So it's a little bit of a side reaction, but it's also sort of like getting stuck in a cul-de-sac. There's this side reaction that happens that's reversible, but you can get stuck in it if it's too acidic.
Right.
Right, so what that means is that there's a sweet spot for the pH. Right around 5.
Okay.
If you get more acidic than 5, your rate drops off. If you get more basic than 5, your rate drops off. Because we need the protons around to protonate the oxygen, but we can't protonate too much of the nitrogen. Now let's split hairs.
I'm just trying to like draw it from right for me.
Yeah, we did. Let's do that.
Is a second just to be a Turner's step first.
Yeah.
But if you think about that.
That gets us our carbonyl.
So a carbon molecule.
Is OL means alcohol, right? And amine means nitrogen. Attached to the same carbon. Carbon, all, amine. They spelled carbon wrong, but you get the point.
Is it supposed to be?
Carbonylamine, yeah, I don't know why. It would make more sense if it was ON, but. Again, they didn't consult me.
It's already. Yeah, in the 8, 7, 10 on.
Alright, so that gets us to our carbonylamine. And then the next step is make a better leading group. And so this is gonna be another case where we're gonna do, no, we're not gonna do 2 proton transfers at the same time. So. Protonate the oxygen again. Make an even better leaving group.
Yeah, and then the nitrogen. Yeah.
And the oxygen leaves with its electrons. So we lose a water. And then they positively charge nitrogen for a second, and then we just deprotonate it one more time. And I think everything else on that slide is right, other than the first step.
Yeah, it's not true. So all that just to change the oxygen to a nitrogen
Basically, yeah.
and
It turns out adding nitrogen in the right spot is a really big deal sometimes. That's the difference between pseudoephedrine and meth, for instance.
Great.
So. Yeah, and that's obviously a legal example, but relevant in pharmaceuticals and in biochemistry as well. The ability, and so there are enzymes in our body do similar reactions to convert, say, adrenaline into serotonin or adrenaline into dopamine.
Okay.
Things like that. The big difference between them sometimes is just the nitrogen in the right spot.
So does our body take like the adrenaline, like after the moment has passed and turn it into release?
So, a little bit. So adrenaline and dopamine both have pretty similar structures, just with an extra OH in the right spot. Trying to think I think that there's an extra OH is the biggest difference. And that's why one of the reasons why an adrenaline rush can feel so good is because when you produce a ton of adrenaline, it gets you ready for flight or fight.
Right.
But it also, some of it is being converted into dopamine at the same time. So especially for people that are, adrenaline junkies, they like that rush of the flight or fight.
Yeah.
Because it also triggers a release of dopamine.
Yeah.
All right. That only works if it's ammonia or if it's a primary amine as our nitrogen file. If we have a secondary amine, meaning it has two R groups instead of just one, that's not going to work because we don't have. Go back for a second. We had to be able to kick two hydrogens off for this to work, right?
Yeah.
We kick one hydrogen off to make the carbonylamine, and then we kick another hydrogen off down here to make the imine.
Yeah.
We can't do that if we don't have two hydrogens.
Okay.
If we have two hydrogens, we can still do a dehydration reaction, but it's not going to make an imine. So, because if we stop at the carbonylamine here, we get something that looks like, there's our OH. Something that looks like this, right? Since we can't kick off another hydrogen, it'll still do the next step where you lose the OH group and you make a nitrogen double bond. But that nitrogen has a positive charge, so it doesn't stay there. So what happens instead is it does a little rearrangement. We're basically going to kick off one of the hydrogens from over here. Since the nitrogen doesn't have two hydrogens to give up, we kick off a hydrogen from an adjacent carbon, from an alpha carbon. All right, so everything's the same up until here. But instead, that last step is all that's different. Because for that last step, if we're trying to kick off one more hydrogen, it has to be a hydrogen from an alpha carbon. And so that gives us a similar product, but instead of an imine, we get an enamine.
Okay.
En means what? Alkene.
Oh.
Just basically, they did the same thing with enamine that they did with enol. Remember, enol was when you had an alcohol attached to an alkene, and enamine is when you have an amine attached to an alkene. Yeah. Enamine formation. Yeah. And so it's going to be mostly the same. It's pretty much the same mechanism, pretty much the same clues on your reaction arrow, except your amine is secondary. It's got two carbons attached to it instead of just one. So you make the imine, the imine. That's why I like imine a little bit better. It's less consistent, but it allows us to distinguish between imine versus imine. If it's going to make an imine, it has to be either NH3 or have at most one R group.
If you have an amine that has two R groups, it makes an enamine instead.
So the difference between an IV is one R group versus two R groups.
Exactly. And the mechanisms are identical up until that last step. Yes, we're doing fine. We have one more reaction to add, so we can stop and do some practice since we've added a bunch of reactions today.
What's the product?
Just the products.
And the R group, right? Yeah. I it's the double bond.
That's secondary. It doesn't have two hydrogens that it can lose, so you're not gonna make that imine formation, right? But what about this?
I'm being on time to go on that second side.
Fair. Yes.
I look.
So nitrogen, already in the same molecule.
Yeah.
Our two reactant groups in the same molecule means we're gonna do ring formation.
Oh,
Because we can do that, right?
yes,
Is this nitrogen primary or secondary?
I
So does that mean imine or imine? Imine. So we're gonna get a 1, 2, 3, 4, 5-sided ring.
Oh, because the nitrogen is in the ring. Oh,
Okay, it's part of the ring. And it's gonna form a double bond, this is an imine, right? So this is the carbon that has the oxygen attached. So there's one more carbon there. And then one carbon away from the nitrogen. So one carbon empty, and there's our two metals. So how did the middle one go?
I think we got it. We did the original house with is replace the O with the hydrogen and then add the house that's attached.
Good. So this one is primary, so it's gonna be the imine formation.
Which means we're just replacing the oxygen with the nitrogen,
Whatever's attached. This is about as complicated as they can get.
Okay.
Right, when with the ring formation and the other substituents attached, we just have to be really careful that we remember where everything is placed. And we keep track of, okay, this is the carbon that the nitrogen attached. And then count from that to figure out where everything else goes.
Yeah, it's in the miles to that.
Yeah.
All right, how about top right? Or should I give you a few more minutes? Few minutes, we'll go through those. The last reaction
Will not only take about 5 minutes, so we're okay to do pace pounds.
get some practice.
Is it similar to these ones?
Kind of.
Okay.
It's carbon based, but it has a similar net effect as the imine formation.
Is that what you're saying? Yes. Yeah, why not? That is fun.
Salvation. Acidic conditions, excess alcohol here. Alcohol is your nucleophile. That says minus H2O tells you you're going to kick off this first oxygen and replace it with 2 F oxygens. Here's one that's going to look like our glucose ring formation. You got an alcohol. It is going to form a ring.
Oh, shit.
We've got an alcohol and our carbonyl on the same molecule. Question is just going to be how big of a ring. And don't forget to count the oxygen because the oxygen's in the ring. 1, 2, 3, 4, 5, 6. One of the carbons, because there's no other branches or anything else in this, it doesn't matter if I put it here or there. But we will see the carbon that is part of the ether has an OH on. One of the carbons that is part of the ether will have an OH on. This is the oxygen that was the aldehyde.
No, I'm just like, I don't know, I feel like going back and watching this.
There's just a lot of little details to keep track of.
Yeah.
All right, last one. Let's undo the acetal formation. We're starting from the acetal and we're giving it lots of water under acidic conditions. So we're going to remove the acetal and turn it back into a carbonate.
Why couldn't you say? Are you trying to learn specific sounds? Yes. The same amount of words there are English. There's, I'm learning so many words in vocabulary. It's hard to keep track of. Okay, this is a language. That's
Yes.
what I'm saying. It's like learning 2 languages at once.
So Kuiper's getting ready to go to TK next year.
Okay.
At BSU, so it's going to be in Spanish. So he's starting to comprehend the fact that Spanish is a different language. For a while, he was making up noises and saying, that's how you say it in Spanish.
Of course.
But now he's like, well, how do you say this in Spanish? Like I quizzed on my high school Spanish the whole way to daycare this morning. How do you say tree? How do you say dirt? How do you say bumblebee? I got most of them. I don't know leaves. Abeja.
How do you walk?
I took a lot of Spanish in high school and college. I would have been a Spanish minor, except that at my school you had to study abroad in order to be a Spanish minor. And that would have put me back a whole year because I can't take chemistry class in a Spanish speaking. Yeah. So it wasn't in the cards, but I did take a lot of Spanish and I remember most of it. I remember most of the vocabulary.
It seems like I remember most of it.
Don't ask me to conjugate things in the subjunctive, but other than that. All right, last reaction. This is a named reaction, like the Grignard reaction. We get to practice how to pronounce things in German. Actually, I think it's Eastern Europeans for sure. I do not think it's German. It's pronounced bitte.
Oh.
W is pronounced with a B in Russian in a lot of Eastern European languages. So the Russian way of spelling vodka is like that. So the bitte reaction, same net result as our imine formation. We remove the oxygen and replace it with our carbon. So we take, but this is our bitte reagent.
We started writing them on and stuff. What? Okay. What are you writing? What words are you writing? Where is there a P in that? Taylor. Literally. Oh. What are you? I can't even like say the word, and I just like. You can see where the confusion came. I can see where the confusion came.
All right, and so this is a really kind of a special case. We do have a mechanism for it. What makes it tricky is that it's a cycle addition. Sort of like oral hydration, or the hydroboration rather, where we add, you basically get so that it lines up with phosphorus to an oxygen is a more stable bond than a carbon to an oxygen. So we're basically going to swap the carbon for the oxygen. And it all happens at once. So it's a quick mechanism to draw, but you have to realize you're going to make this intermediate that looks like a four-sided ring.
Okay. So the carbon for an oxygen or the oxygen for carbon? Oxygen.
Oxygen for a carbon. From the phosphorus point of view, it's swap carbon for oxygen. Yeah, I'm just giving you a hard time. All right, so your clue for this one is you got to be able to recognize the Vidic reagent, which sometimes is drawn with the double bond between carbon and phosphorus.
Why?
Because it's a valid resonance structure. A carbon with a negative charge has a lone pair, and phosphorus can accept another pair of electrons. But either way, when you see phosphorus with all these phenols attached, you should be thinking Vidic. And these two hydrogens can be R groups too. So it's a way to add to link the two molecules together.
Let's solve. What? You. Oh my goodness, dang. What? You. What am I gonna do in a submarine?
What?
That song. Does that arrow point to the P or the line? Or the first arrow is the mechanism?
I just confused something. Hang on.
Like the P.
There it is. Okay.
Say the P. We have never draw arrows towards other electrons, right?
Well, except
Except for what?
free radicals.
Free radicals. But then it's not a double barbed arrow, it's a single
That's
barbed arrow.
I was watching a video on them and it called it a fish hook arrow.
Yes.
I mean, I got it.
The barb on a fish hook looks like that.
Yeah, yeah.
A double barbed fish hook looks like that. So take your pick, fish hook arrow, single barbed arrow, same thing.
I think. Still barely. But now you make for the. Into.
That is true.
All right, I'm just double checking. I think that you're gonna have to do a little research. I think there's one question on the quiz. If I'm remembering right, so I looked at the quiz before I got the lecture. And I don't think
Yeah,
there's one that does it, that doesn't have this, we haven't talked about yet. You're gonna have to look up the reaction for rainy nickel.
Rainy nickel.
Rainy nickel is the, actually I think it's EL.
Should we take notes on it? Like,
Yeah, like it might show up again. I believe it's just a hydrogenation reaction. I think it's just a way to do a reduction of a carbonyl. But we didn't talk about it. So if I'm remembering correctly, one of the questions on the quiz says rain nickel as a catalyst. So do some research, try and answer that one on your own, and we'll go over it next week.
So, and like in this chart, 14 is the city.
14 is the bid agreement. 14's over here.
Yeah,
If I didn't, I don't think I pulled this one out yet. If I get a chance today, I will pull this out as a JPEG and put it in the week overview.
Yeah.
So that you have your shortcut. Yes, 14 is bidding. So this is the other way that you see them drawn. Without charting, just CH2, PH3.
it's the PH3 that I know.
Yes. Correct.
PH plus.
Triphenyl phosphorus.
The speaker. About like